This is an ABC color presentation.
Walt Disney's Disneyland. Each week as you enter this timeless land, one of these many worlds will open to you. Frontierland. Tall tales and true from the legendary past. Tomorrowland. Promise of things to come. Adventureland. The wonder world of nature's own realm. Fantasyland, the happiest kingdom of them all. Presenting this week. Here to introduce you to this new series is Walt Disney.
In our modern world, everywhere we look, we see the influence science has upon our daily lives. Discoveries that were miracles a few short years ago are accepted as commonplace today. Many of the things that seem impossible now will become realities tomorrow. One of man's oldest dreams has been the desire for space travel, to travel to other worlds. Until recently, this seemed to be an impossibility. But great new discoveries have brought us to the threshold of a new frontier, the frontier of interplanetary space. In this Tomorrowland series, we are combining the tools of our trade with the knowledge of the scientists to give a factual picture of the latest plans for man's newest adventure. Here's Director Ward Kimball to tell you about it.
In working with engineers and scientists, we have found that there are many different opinions as to how we will eventually cross the space frontier. However, there's one point all of them seem to agree upon, and that is whether we use chemical fuels or atomic energy, it will be a rocket-powered ship that will finally take man into space. So, to set the stage for the part the rocket will play in the coming conquest of space, our artists have searched back through history and traced the rocket and various space travel ideas from their earliest beginnings. The first thing we found out was that the rocket is not such a modern invention after all. In fact, its history began way back in the 13th century. It was in China, to be exact, at the Battle of Kai Feng Fu. A little over 500 years later, Sir Isaac Newton explained this phenomenon by saying, "For every action force, there is always an equal but opposite reaction force." Sir Isaac's statement can best be illustrated by showing what happens to our pet dog when he sneezes. For every action, there is an opposite but equal reaction. This same principle applies when we light an ordinary skyrocket. Action, reaction. However, gunpowder is not the only propellant that demonstrates the action-reaction law. There was a time when steam was seriously considered as a means of rocket propulsion. Typifying this idea was Charles Golightly's aerial steam horse. Early inventors soon realized that steam rockets would be too heavy to fly, so they returned to designs utilizing gunpowder. These ideas made many successful flights, on paper. In 1865, Jules Verne fired the imagination of the world with his first book on space travel. It was called From the Earth to the Moon. Mr. Verne used a very interesting device in getting his heroes to the moon. He shot them through space inside an enormous artillery projectile. It was Verne's story that inspired George Méliès to create the first space travel motion picture in 1902. first man to associate space travel with the use of rocket power was Hermann Gansfind. His idea was to have the rocket pull the ship instead of push it. This conception was quite unique, but only an inventor's dream. However, a few decades later, a real milestone in rocket history was passed when the American professor, Robert H. Goddard, introduced a liquid fuel rocket, which used gasoline and liquid oxygen instead of gunpowder. This small forerunner of our large present-day rockets actually rose 60 feet into a wintry New England sky. These experiments led to the founding of the American Rocket Society to advance the science of rocket propulsion. At the same time, the German professor Hermann Oberth wrote, "Theoretically, there is no limit to the size of a rocket which uses liquid fuel." In 1929, Oberth designed a giant rocket ship for the Fritz Lang movie, Frau im Mond. The Girl in the Moon. During the late 1920s and early 30s, we saw an era of feverish activity among the rocket experimenters. Almost every type of vehicle was adapted to rocket power. Here is the first successful flight of a rocket-powered airplane. Rocket-powered autos were fast, but presented quite a smoke problem. There were railroad rockets and nautical rockets. Some fired and some backfired. These early attempts met with varying degrees of success. Meanwhile, in Germany, a group of serious-minded engineers founded a new society for space travel and succeeded in building rockets which finally reached an altitude of 1/2 mile. Soon after this, the German Army established its own rocket program. The development of the first rocket missiles followed. This accelerated rocket program culminated in the creation of the forerunner of spaceships to come, the V-2. Even though there were a few mishaps, the V-2 emerged at the end of the Second World War as the most successful rocket yet devised by man. 75 of these captured V-2s were brought to our rocket proving ground at White Sands, New Mexico in 1945. Here, exhaustive studies and test firings were made to aid us in mapping our own newly created rocket program. It wasn't long before the sands of New Mexico shook to the roaring blast of the Viking, the Corporal, the Aero Bee, and other American rockets. rocket firing is an awesome demonstration of tremendous power. I think we should find out how it works. One of the best authorities on this subject is the rocket historian, Willy Ley. Here, Mr. Ley explains the operation of a rocket motor to some of the artists working on the picture.
This is an actual propulsion unit from a V2. And this strange-looking device is both the heart and muscle of a rocket, its motor. Now, all earthbound engines have to burn oxygen from the surrounding atmosphere. But the high-altitude rocket motor has to work in outer space where there is no oxygen. To overcome this, we carry a tank of liquid oxygen here. When burned with a fuel, in this case alcohol, it produces an intensely hot, torch-like flame that would quickly melt the motor. However, we cool the motor by first circulating the alcohol fuel around it, until this fuel finally reaches the point where it is sprayed, along with the oxygen, into the combustion chamber. When this steady flow of alcohol and oxygen is ignited, it produces a continuous explosion which blasts the rocket away in the opposite direction. Here again we have action and reaction. If this motor is placed in a streamlined hull with suitable controls, it can reach a high altitude in a very short time. The V2 rocket motor only operates 65 seconds to a height of 20 miles. But then the V2 has gathered so much speed that it will coast upward to an altitude of 114 miles before gravity begins to pull it back to Earth. Notice that the rocket does not nose over in the thin upper air, but it falls tail first until it re-enters the denser atmosphere where the air, acting on the tail fins, turns the rocket nose down. Early in 1949, space history was made when the payload in the nose of a V2 was a small rocket called the Ward Kimball. When the large V2 reached its maximum speed, the smaller rocket was ignited. This additional boost in speed enabled the Ward Kimball to set a new high-altitude record of 250 miles. This day marked the first time that a man-made object reached outer space. This was accomplished by using a double rocket, then secretly known as Project Bomber. However, we refer to it as a two-step or two-stage rocket.
Is it possible to build a three-stage rocket?
Yes, as a matter of fact, that's the next logical step. Here's a rocket I have designed that has 3 stages. It would stand about 70 feet high or a little taller than the old V2. Here you can see the 3 sections, each one having its own rocket motor. If somebody will please make a sketch for me, perhaps I can explain how it will work. Good. Here we show our rocket in its launching position. The first great blast starts to lift it. And after gaining initial speed, the first section is cast off at 20 miles up. At 45 miles, the second stage is released. The third stage now fires until it reaches an altitude of 70 miles. At this point, our rocket has now attained a tremendous speed and the motor shuts off. Its forward momentum would carry it straight out into space if it were not for the Earth's gravity. This downward pull of gravity bends the upward course of the rocket into a curved path. And if the rocket's speed going away from the Earth creates enough centrifugal force to balance this pull of gravity, our rocket will continue coasting in its curved path around the Earth indefinitely.
Mr. Ley, is there another way we can illustrate this?
Yes, let's explain it this way. If the rocket were to move at a slower speed, the pull of gravity would soon overcome the rocket's momentum and it would return to Earth here. If we add a little more speed, the path of the rocket becomes longer. And it goes farther before it returns to Earth here. So if we have our rocket go fast enough, it will eventually follow a curve which matches the curvature of the Earth and will not fall back. We might say that the rocket falls around the Earth as long as it maintains sufficient speed.
But how does it maintain this speed with the motor shut off?
Remember, our rocket is traveling above the atmosphere in space, where there is no air friction to slow it down.
How fast does it have to go to stay up there?
Now that depends on how high we want the rocket to be as it circles the Earth. Let's use the altitude of 1,075 miles. Because at this height, the rocket will have to go nearly 16,000 miles per hour and will make a complete trip around the world every 2 hours. A few adjustments in its course will be necessary, but this can be accomplished from the ground by remote control, after which the rocket will continue to coast freely in space forever.
In other words, the rocket will stay up there just like the moon.
Yes, it will circle the globe as a man-made satellite.
What is the purpose of having this satellite up there?
Having this instrument-carrying rocket moving around the Earth will give us a lot of important information which we'll need before we dare let a man make his first trip into space. To run the scientific apparatus contained in the satellite, a mirror will focus the intense rays of the sun onto a silicon battery, converting solar energy into electricity. There will be a television camera to give pictures of the Earth as it appears from 1,075 miles up. We will collect very important data on the effects of the mysterious cosmic rays. Even hits by meteorites the size of a grain of sand will be recorded. Every 2 hours, when the rocket moves over the North Pole, its radio will transmit a stream of data to a receiving station below. This will be the first outpost in man's conquest of space.
One of the big question marks of future space travel will be man himself. How he will react mentally and physically to this unearthly experience is the concern of a new field of science called space medicine. Helping us illustrate this interesting problem is the scientist most noted for his pioneering work in space medicine, Dr. Heinz Haber.
When man steps into his rocket ship and leaves the Earth behind, he must be well equipped to survive in the hostile realm of outer space. To portray the complex problems of space medicine, we have designed a sort of common man. A man just like you and me. We will find out what will happen to him on a trip into space. In a way, he's going to be our space guinea pig. That makes him a brand new biological species. I think we should call him Homo sapiens extraterrestrialis, or spaceman. Since he was picked at random, we cannot tell whether he will be able to tolerate the tremendous stresses to be placed upon him when the rocket ship is fired into space. He gets an inkling of these stresses when he rides in an automobile. When he steps on the accelerator, the car moves forward and he is gently pressed against the back of the seat. His body resists any change of motion. When he comes to a stop, his body tends to move forward. On a test rocket sled, which is pushed forward at tremendous accelerations, the force of inertia is much stronger. We are all familiar with centrifugal force. We duplicate this force in the laboratory by using human centrifuges. These machines artificially create on man the crushing pressure he will have to endure in a rocket takeoff from Earth. His body weight increases until he blacks out and finally loses consciousness. From tests like these, we have learned that man will have to assume a reclining position when his rocket takes off into space. In this attitude, the stresses will be more evenly distributed along his body. He will then be able to tolerate pressures of up to 9 times his weight or more, as it occurs in a rising rocket. When the rocket engine finally stops, man will face his next big problem, weightlessness. Without support, he will be floating freely, drifting, tumbling, and twisting helplessly. In space, a man, a feather, a bubble, or a piece of iron will have the same weight, or rather, no weight at all. However, man is designed to live with gravity, the down-pulling force which Sir Isaac Newton first explained.
Any two bodies attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Or, what goes up must come down.
Loud alarm signals sound throughout the nervous system whenever we are in danger of falling or stumbling. But weightlessness is not such an unearthly experience. We become weightless for a short while in a dive, on a roller coaster, or in an elevator. But if we remove the support by cutting the cable, we produce the exact feeling of weightlessness in space. It will take iron nerves waiting for the impact that never comes. We can only hope that man in space will eventually get used to this feeling of falling constantly. Without weight, our notions of up and down no longer exist. Man will probably have trouble orienting himself. Confusion such as this is likely to produce nausea. Some people may become victims of a serious form of space sickness. Weightless man in space must learn to guide himself only with his eyes. Beginners can combat dizziness by fixing their eyes upon one single object. The spaceman must learn to move with utmost caution. His muscles are adjusted to normal earthbound gravity. In space, any casual action will be violently magnified. He must coordinate himself under an entirely new set of rules. He can hardly avoid spinning constantly. When he crouches into a compact mass, he will spin faster. If he spreads his arms and legs, the spinning will slow down. After considerable practice, man will be able to master the art of swimming through the air within the rocket ship. For the beginner, a web of ropes might be provided. He must learn that slow, relaxed, careful movements are essential. After his first few encounters with the problems of weightlessness, he will no doubt try to normalize his life. Even the air he breathes will be weightless. Natural circulation of air does not exist, and there is danger of suffocating in one's own exhalations. Air must never be allowed to become stagnant in a spaceship. Circulation must be maintained by constant ventilation. Since all objects are also without weight in a coasting rocket ship, they must be safely secured by bolts and clamps. For handling large, bulky objects, man will have to anchor himself in some fashion. But as it takes force to overcome the object's inertia and set it in motion, it takes equally as much force to stop it once it is moving. On Earth, we are not exposed to dangers from space owing to the protective layer of our atmosphere. But up there, even the hull of the ship would not shield man against the possible hazards of the mysterious cosmic rays. These tiny bullets from the infinity of space will continually penetrate everything. They may prove to be harmful to man. The most energetic of these atomic rays might feel like stings as they shoot through the body. However, there are other bullets in space that may be of still greater concern. Meteorites. These marauders of space travel at speeds up to 150,000 miles per hour. But if one should puncture the walls of the ship, our air supply would rapidly escape through the opening into the vacuum of outer space. Without protection, man could last not more than 15 seconds before losing consciousness. Also, in the intense radiation of the sun, he would soon broil on the one side and freeze on the other. In the void of space, he will have to wear a spacesuit. This specially designed outfit must be a flexible, airtight unit carrying sufficient oxygen. Featuring built-in all-purpose equipment, it will afford protection and maneuverability outside the ship. Propulsion will be by means of a small portable rocket unit. With proper manipulation of this jet device, even the most subtle movements can be made.
Action, reaction.
Dining under conditions of weightlessness will present new and surprising problems. Liquids will be particularly annoying. They will not pour. They must be transferred by titration tubes. This tube will contain the liquid until it is forced into the desired location. Unless liquids are kept in leak-proof containers, they will escape and float in ball shapes around the cabin, finally coating all surfaces with a wet film. Plastic bottles will be used so that liquids can be squeezed out. Food will be cooked in closed containers by radio frequency short wave. Space etiquette will call for the extensive use of sugar tongs. Man can overindulge in space, but he will never be overweight. To relieve the inevitable tensions of space travel, we must provide suitable recreation. A game of three-dimensional pool could be particularly relaxing. Sleeping will be a new and unique experience. A space traveler will not need a pillow or mattress. His bed will consist of a net enclosure to prevent drifting in his sleep. How will man's subconscious mind react to his first experiences with space travel? Will he not suddenly be aware of his precarious situation, trapped in a tiny metal box, floating through the incomprehensible nothingness of space? We do not know. We must plan intelligently if these pioneers of space are to survive and return to Earth safely. The conquest of space will depend to a great degree on the research and findings of this important new field of science, space medicine.
To the engineer, spaceflight poses two problems. The first is, of course, to build a rocket ship. The second, and no less important, is to prepare and train the men who are to fly the future rocket ships and to provide suitable working conditions that will enable them to survive in space. To help show you what is being done to solve these problems, we have called upon one of the foremost exponents of space travel, Dr. Wernher von Braun, who is at present the chief of the Guided Missile Division of the Army's Rocket Center at Redstone Arsenal. He was also overall director of the development of the original V-2 rocket.
The training methods for future space flight and the special equipment needed for survival are much like those of present high-altitude flying. And the experiments we are making today are helping us to solve the more complex problems to come. Take the present-day pressurized flying suit, for example. It has been designed for use at extremely high altitudes and is a forerunner of the suits we will wear when we make that trip to the moon. To give you an idea of how engineers and medical men are working hand in hand, here are a few examples of the research that's being conducted at this time. This pressure suit is being worn in a test chamber where the air pressure can be dropped suddenly. Notice that the water boils at this low pressure, even though it is only at normal body temperature. Blood would be the same without the protection of the suit. In other tests, without the suit, where the drop in air pressure is less severe, we see that the body still reacts violently to a sudden decrease in pressure. Lieutenant Colonel John P. Stapp of the United States Air Force has subjected himself to the tremendous forces of a rocket sled that reaches a speed of over 632 miles per hour. The sled stops so quickly that Colonel Stapp's body becomes 35 times heavier than normal. From these tests, we have learned that men can take much greater acceleration forces than crew members of a rocket ship will undergo on a takeoff. Today's aircraft are so fast and so complicated that it has already become routine to train the crews on the ground without risking lives or equipment. This is done with a device called a flight simulator. Here the crews experience all the sensations of an extended flight. The crews of future rocket ships will train much the same way. We will use a simulator on a centrifuge and employ an astrosphere to train the celestial navigators for our coming space flights. Now here's a model of my design for a 4-stage orbital rocket ship. Compared to the unmanned instrument rocket, it is quite large. But the overall size and weight of the rocket is mainly determined by the 11 tons weight of this top section. This weight dictates the amount of fuel and the numbers of motors needed to produce enough power to equalize the gravitational pull of the Earth. The payload in the top section will consist of 10 crew members plus equipment. Notice the wings, small rocket motor, and landing gears. This is a section that must ultimately return the men to the Earth safely. To produce the energy needed to hurl this stage into the orbit, we need these 3 additional rocket-powered sections. Here we have a cutaway drawing of our rocket showing the location of the fuel and the motors of each section. The first stage carries 1,060 tons of fuel, and its 29 motors will lift the entire weight of the ship vertically off the ground. The second stage has 8 motors and carries 155 tons of fuel. It will be dropped when its speed has reached 14,300 miles per hour. The next is our third stage, with only 1 rocket motor and 13 tons of fuel. The third stage gives the passenger section the final kick to attain the orbit. It will not be separated from the passenger section until just before the return flight. The third stage will be left in space, and a very small motor in the winged fourth stage will return the ship to the atmosphere so it can glide back to the base. If we were to start today on an organized and well-supported space program, I believe a practical passenger rocket could be built and tested within 10 years. Of course, it would be foolish to rush headlong into building a 4-stage rocket, man it with a crew, and attempt to fire it into an orbit without first following a step-by-step research and development program. Let's illustrate this with the help of a few pictures. First, we would design and build the 4th stage, and then tow it into the air to test it as a glider. This would also allow the crews to practice. Next, low-altitude flights would be made, firing the small rocket motor in the fourth stage. This would also give the crew more and more training. Following that, the third and second stages would be constructed and tested very thoroughly on the ground, after which they would be joined to the passenger section so that faster and longer flights could be made up to speeds of about 12,000 miles per hour. The only thing remaining would be the building and ground testing of the huge first stage. Then there would be no more test flights. When all the sections are joined together, the ship and its crew will be ready for man's first flight in space. Let's look ahead a few years and see how this might be accomplished.
There it is, a small atoll of coral islands in the Pacific, where man is dedicated to just one cause, the conquest of space. Here below us, a small city has been created to house the scientists, engineers, and technicians on whose shoulders rests the tremendous responsibility for this great adventure. This is the Rocket Assembly Building, with tracks running to the launching site. Only 48 hours remain until firing time. Our spaceship moves ponderously toward the firing site. After the ship is securely anchored over the blast tunnel, the elevator's spar is raised into place for the final pre-flight check and fueling. This is the blockhouse, the control center for Operation Space Flight. Here, the oscilloscopes, radar scopes, computers, and tracking devices are the brain and nervous system for the rocket. Dancing patterns of light will record every detail of the blast-off and climb into space. In the windowless blockhouse, observation is by periscope. Through a system of worldwide radar stations, electronic eyes will always be focused on the rocket as it orbits around the globe every 2 hours. The tracking radars report ready and are standing by. The optical tracking stations are poised and ready to follow the rocket in its upward flight. As 0 hour approaches, the painstaking work of the checkout crew continues. The ship and every piece of its equipment is being checked and rechecked.
Blackout, can you hear me? Will you give me that stage 2 separation signal again? Okay now, over.
Now swivel motor, stage 3 to pitch right. Okay, now give me the left.
Attention all personnel. It is now X minus 2 hours. Fueling crew, take your stations. Safety area will be cleared by all personnel.
In the pits, the required quantity of fuel is preset. The pumps will deliver 1,230 tons of hydrazine and red fuming nitric acid into the tanks of the waiting rocket. It is now X minus 20 minutes.
Flight crew, report aboard rocket. Flight crew, report aboard rocket.
After years of careful preparation, testing, men and materials, this is the final payoff. Now, man will bet his life against the unknown dangers of space travel. Human reactions are not precise enough. Therefore, once the launching timer is started, the entire takeoff and flight into outer space will be controlled automatically.
X minus 5 minutes. Clear the firing area. Clear the firing area.
X minus 90 seconds. X minus 30 seconds. X minus 20 seconds. X minus 15 seconds. X minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
The total firing time has been 5 minutes. The ship will now coast for 51 minutes before the adaptation maneuver begins. At over 60 miles above the Earth, the crew members experience the sensation of weightlessness for the first time.
Blockhouse to XR1. Your cutoff altitude is 63.9 miles. Distance from launching pad, 705 miles. Velocity, 18,467 miles per hour. Angle of elevation, 4 minutes of arc. Plane of your ellipse of ascent incline, 66 degrees, 32 minutes, 2 seconds to plane of equator. Out.
51 minutes later and halfway around the world, the rocket is coasted to its maximum altitude of 1,075 miles. Its speed has diminished to 14,770 miles per hour. The navigator must now take a bearing on 2 fixed stars. He will line up the ship for the adaptation maneuver, which will drive it into a circular orbit around the Earth. Electronic controls will fire the rocket motor at the exact second the ship reaches the proper position. The ship and crew are now coasting freely and silently through space. Here, man is no longer earthbound. From his new vantage point of over 1,000 miles high, he sees the Earth as a vast rolling sphere, upon which the oceans and continents are reduced to simple patterns of light and dark. Great cloud formations will appear as small patches of snow. Evidence of man's existence is almost invisible. Large cities can be seen only with the aid of powerful optical equipment. Meteorologists will make studies for long-range weather forecasting. The science of astrophysics will welcome the clear views of our moon and planets, unhampered by atmospheric disturbances. Space medicine will benefit from tests conducted with new type spacesuits.
Air Force Keflavik Iceland calling XR1. We have you in radar contact at 107 miles due south this station at 29. Estimate you at Prestwick Station Delta at 37.
Tests and observations by the crew will lay the groundwork for the future construction of a space station and will add to our knowledge of many sciences.
Instrument rocket approaching from 3 o'clock high.
At a pre-calculated time, the rocket's path will cross that of the instrument carrier, sent into space a few years before. 22 hours after takeoff, our spaceship has made 11 revolutions around the world. It is now time to make the return trip. The engineer releases the third stage. It'll be left circling in space. All tests are now concluded. The navigator checks the ship's position for return firing. 1 minute to go. The automatic firing timer is set. The ship is lined up so the blast of the motor will be against its forward motion. This will slow the rocket's speed and cause it to begin its long glide back to Earth. The ship is now moving 1,000 miles per hour slower. After coasting halfway around the world, the rocket will leave the vacuum of space and sweep into the upper layers of the Earth's atmosphere, where air friction will gradually reduce the rocket's speed. When the ship drops to an altitude of 50 miles, air pressure will build up on the control surfaces. For the first time in the entire flight, the captain will be able to fly the rocket as a normal plane. Air friction begins to send the skin temperature of the rocket climbing until the ship glows cherry red at 1,350 degrees. The double hull and refrigeration keep the crew from perishing. The returning rocket continues the long glide down into the lower atmosphere, its temperature gradually dropping to normal as airspeed diminishes. Mission completed. Man has taken his first great stride forward in the conquest of space. His next goal will be the exploration of the moon, then the planets, and the infinite universe beyond.